Hello guys, Cyprien from FEA, and this is the second part of the nonlinear spring tutorial with Salome Meca. If you haven't watched the first part, I highly recommend you to go back and watch that, because it's really necessary to understand all those first steps that I have done in this first video before watching this one. So in this video, what we will watch is how to create a beautiful mesh for spring model. So this is necessary when you want to work with contacts and when you want to get really accurate result in terms of stresses and and get the convergence of the solution. So that's what we'll do. First, I'll do a very good mesh, and then I'll show you how to assign the contacts and how to make this model converge. And along the way, I'll show you how to find more information about those different types of contact in Salome Meca and Codastr, and how to solve various kind of problems that you will encounter. So I hope this will be useful, and if you have any question, if you think something is not presented in this video, or if you simply want to to say thank you for these beautiful videos, so please leave a comment and let me know. This is very useful, and I like very much to read that this is useful. So let's go for the tutorial. Here's the problem we're gonna tackle. So the spring is here, and we are gonna apply a load of 4 mm displacement in the Z direction on the top face. There's a plate which is fixed on both sides. Material of the spring is steel, and it's an elastoplastic nonlinear material. So I've shown in the previous part of the video how I assign that. And of course, there's the contact in between the spring and the plate, which will be the main difficulty in this simulation. Okay, so now I'm back to Geom module, and I want to modify this model and make it much better for simulation. So first of all, we have to see a bit what is worrying in this model. So there are several things that I think are not very good. The first one is, as you can see, there is a gap in between the plate and the spring. So if you want to apply contacts, it will be pretty difficult, because you'll have to take in account the initial gap and set up something so when this enters in contact, it starts to apply the contact and everything. Basically, it's very complicated. So what I'll do is that I'll find a way to basically place these springs very close to the plate. The second thing is that this plate is a 2D plate, so it's a shell, and again, making contact between a solid and a shell is doable, but it's a bit difficult. It's not very straightforward. So what I'll do is that I'll make this plate solid. So I will basically extrude that. And now there is a third thing that I think is not very good, is that if, just imagine this plate, I make it a solid, I make it very close to this. The part where it enters in contact at first is just a line. It's the line of this contact face here. So basically there's just a line of contact at first. So I guess it's doable again, but it's probably easier if I extrude a bit this part here, just to make it bigger, so that at the initial stage there will be a real plate-to-plate contact on this part. Now finally, this model, I want it to have very good mesh. So I like to mesh it with hexa element, and the way it is constructed right now is that if you're looking at those areas here, there's just a line here. It's not in here. It's a full solid. So basically, it's not a block. So I have to divide this into a block or several blocks. So I'm able to use the hexa mesher and split that into hexa mesh. It's also very thin, so controlling the number of elements on the thickness will not be easy. But let me show you how I did all of this, and you will understand how to make this kind of model a bit better to work with. So let's start with extruding a bit those two edges. So how can you do that? The first thing is, for the extrusion I need a plane that will be placed exactly on this face. So I need to use a tool called explode to basically select this solid, and I want to extract some of the faces, and you can select which faces you want actually to extract from it. So let's select this one, and let's rotate that. I'm always having trouble with the buttons. Okay, shift click to select this. So now I have those two surfaces. If you show only selected, you'll see that it works. It's only selected those two. So now I can apply and close, and you see that in the work tree here, in the object browser, I have those two faces that appeared. So now I can extrude those. So let's go into generation, new entity generation, extrusion. Let's select this face first and extract it along. So this is the x-axis, and let's see what's appropriate. 0.1. No, yeah, it's in meta, right? So 0.01. Maybe it's a bit too much. 0.05. Yeah, that looks okay. So let's extrude this. Okay, like that. Let's do the same on the other side. So the base will be this, face 1, vector will be this, and this time I have to put the minus. Okay, apply and close. Okay, so that's done. So it's true that I'm changing a bit the shape, so but if you consider that this part will be in contact, and the stress will really happen in that region there, this will be more or less, this will only slide, and it won't really get anything. I don't think the result will be very different, but what you can do anyway is that once you able to simulate that, you can always change back your model and delete this part and try to get it work without this. So I don't think this is a big problem. Okay, so now I got this done. So let's go and work on splitting a bit this this body here. So to split this, I'll have to create some planes. So let's go into new entity and basic plane, like that. And the way to select a plane will be, so you can choose a point and a vector. So let's try that point. I want to split it along x-axis, so like this. The plane is a bit too large, so let's try 0.1. 0.1 is 0.05, like that. Okay, so that's apply. So that's one plane here, and I have to construct like that several planes on each of those places. So one here, one here. Let's put one here. Let's put also one here. And I need also here. Okay, now let's think a bit. So if I divide this model by those planes, this is I should have a good division in blocks, but this part here is still not divided in blocks, so I also need to split those in two, like that. So for the moment, let's hide the planes that I just created. I'll show them a bit later. Let's create one plane here, and this at the middle. So how can I do that? Point here, same way. So I got one like this. Now I need to create one in the other direction. That will be, actually I'll divide, maybe I just divide the whole model in this direction. So yeah, let's do that. Anyway, yeah, I have to divide the whole model. So let's select the origin and let's select the Y vector, and that time I need to make the plane bigger. So it takes the whole model. Okay, apply, that's done. And now if you look at this part here, you have to count how many edges it has. 1, 2, 3, 4, 5. So I need to split it in half as well to have to make it into blocks. So I need to create 2 last planes. So to create those planes, let's use this like that. Let's select the points like this. So I can put again 0.05, apply, and one on the other direction, apply and close. Okay. Okay, so now let's show up all the planes that I created, and it's time to divide this model. So let's hope it works. Let's save that, and to do that I have to use partition. So let's choose the main object, which will be not the plane but my solid here. My tool object will be the plane from 1 to 10, and just let's apply and close. And yeah, oh yeah, I forgot to I forgot to handle those two. So I need also to that was the plane number 8 if I remember, so I need to divide those two also. Partition, I should have merged those. Okay, so now I got everything is cut. So now, you know, let's do something. Let's try to okay, let's merge that first, those two edge plus this. So to merge those three, let's do a partition also. I think it works. It works also with partition. So 2 object, 3 object, 3 object solid. Yeah, and now if you look, I have one partition which is basically split into everything I need. Okay. Now let's have a look at what kind of mesh this would actually give me, and if the splitting is successful to mesh with blocks. So to do this, go into mesh. Let's have a quick try at this. So I don't know why the object browser disappeared, but I can reactivate it here. So let's do that. Actually, everything disappeared. Toolbars and all the toolbars disappeared. I don't know. That's weird. Okay, so anyway, let's select this partition that I just created. Let's try to mesh that. Let's create hexahedron IGK, and this will be quadrangle mapping, and let's use a wire discretization, and with a local length of so by default it gives me something like that, so I think it's a bit too coarse. Let's try this. This is still too coarse. Let's try this. 2 mm. So let's see what it tells me. Okay, so I am getting some failures, so let's see what is going wrong here. Invalid input mesh, can't find 8 corners of a block, etc, etc. So still it's a bit challenging to mesh like that, so I don't know why. Maybe the size is too coarse. Let's try to change the size. It seems a bit too coarse. Okay, I'm still getting different kind of errors. Okay, so it's not what I want. So let me tell you what I am gonna do. It's much easier to mesh 2D surface mesh, and then there's a feature to extrude that mesh in a specific direction. This will allow me to get very, very good mesh. So let's delete this. Let's go back to my geom module, and I'm gonna use the explode, sorry, it's called explode all of this, and I'm gonna explode the faces, and I only want the faces of the top, so I have to select all those faces. So I'm pressing the shift key to get everything selected. Okay, apply and close. So let's hide the partition, and you see that I have only the mesh on the top right now. Now, if I mesh those, what I could do is mesh one by one each of this face, and then, you know, sew them together as a mesh set, but that's a bit difficult. So what I prefer to do is to use a Boolean operation to, or yeah, I can use also this partition, right? I can do a partition of all those faces, and the result will be a shell. So it has 25 objects. Is it the correct count? Looks like, oh, it selected also this, so it's not, I only want the faces. 24. Okay, apply and close. Okay, now I'm getting one partition. Let's try again in the mesh to see what this provides when I try to mesh that. So quadrangle mapping, Y discretization. Let's try the same local length. Compute. So this time I have no error, which is a good news. And we can see that the mesh looks like this. So on those areas it's perfect, but the mesh here is very strange. And why is it like this? It's like this because I am controlling the size of the size on each of those edges should be the same. But if you think about what a good mesh is, you want those elements to be always almost the same size, but I mean, you know, aligned here. Yeah, that's what I mean, aligned. And so the size goes from this kind of size to a bigger size. So the size is not constant, not the same everywhere. So instead of controlling the size, I have to control the number of elements in this area here when I mesh. So in order to do that, I have to use sub mesh to create sub mesh on those edges. So let me show you how to do this. So I need to have edges on that. So let's clear the mesh. Clear the mesh data. Let's go back to geom, and I have to create groups on this partition here. So create some groups, and let's select the edges here. Oh yeah, okay, I have to select edge group. Let's select the edges here. Let's add that, and this will be center. Let's call that center edges. I don't know, you can call it as you want. Apply. Okay. Now that I have this, let's go back into the S-mesh, and on the mesh set that I have here, I will create sub-mesh, which so the mesh will be mesh 2, the geometry will be center edges, and I want a wire discretization. This time I will create number of segments, and let's try with 10 to start. Equidistant distribution, okay. So let's try that. Let's try to remesh everything. And wow, now it's looking very good. So as you can see, now that the number of elements are controlled on each of those edges, looks much better. Now the only thing you can say is that if you look at here, there is a difference of size to accommodate the size here and the size here. So if the size of those elements and the size of those elements is the same, that would be even better, because I wouldn't have those triangles here. So let's measure what is actually the size of those triangles. Measurement, measuring distance. Let's see what is the distance between this and this node and this one. Okay, node. Oh, okay, I have to select node 436 and yeah, compute. So this is y direction. So in dy direction, this is the size. So let's set up this. Yeah. You know what? Instead of controlling the size everywhere, I can create a second group of elements. You'll see. I can control the element size on those edges as well, so that way I'll get the same size here. So that will be much better. Let's go back to geometry. Let's activate again this partition here. Let's create some additional groups, and this time I want to select those those 3, 4, 6, and yeah, okay, add that, and this will be, I don't know, y edges. Let's call that y edges. Okay, let's go back to my mesh. Let's add another submesh based on this y edges and I will choose wire discretization and number of segment. That way the number of segment here will be the same in the middle. So if I clear and compute again, Now, you know, it's going very good. So I'm getting exactly the same mesh size everywhere, and you see the mesh is very clean. Okay, so first step of this meshing is done. So to extrude this, let's go back to my geometry. Let's activate again the initial lift spring, and let's look at what was the thickness of this part here. So inspection, dimension, minimum distance, apply. That's where I don't know what it did. Okay, so that's the distance here, 0.00127, so 1 millimeter 27. So let's take some notes. Let's note that somewhere, because I'll have to divide this by 3 to extrude it correctly. So 1.27 millimeter. Okay, noted. Then, now that I have this, let's go back to my mesh and let's extrude this mesh. So to extrude the mesh, select this, go to my modification tab, and you have extrusion. Now, what do I want to extrude? Nodes, edges, faces. Well, faces. And in which direction? So in so Z direction, right? And you have number of steps. So number of steps 3. So which means I want 3 layers. The thing is, the value I have to input here is the 1.27 millimeter divided by 3 that I just calculated previously. So let's take the calculator, 0.00127 divided by 3. So this is what it tells me, 0.00042333. So 0.423. Okay, so there's only one. That's maximum number of digits. So let's round it to 42. And let's try apply, and it worked. So you see now I'm getting a beautiful spring with those 3 layers of elements here. Okay, now we need to extract the plate. So let's you know what the thing is, that I have this plate, right? If I activate it, well, where is this plate? Face. Yeah, that's it. Let's mesh that plate. So this is my face. Let's create a mesh set. Let's have quadrangle mapping, wire discretization, and I want a local length. So what the value I had here was 0.005. So the mesh size for this plate should be larger than the mesh I have here for those elements, because this will be the master contact. Master contact is always larger than the slave contact. So let's try 0.001. Maybe that's a bit too large, but you know, we'll see. Compute. Okay, so that's actually a bit too coarse, I think. If I have a look, that's almost same size as the mesh here. Maybe I'll increase that just a little bit. Let's try 2. Okay, that's that should work. Well, in theory that should work. So let's go with that. So now that I have meshed this face, I can get the exact distance between the node here and the plane here. So measurement, minimum distance, let's have a look at this node here. And I know, let's select a node here. Anyway, I'm only looking at the DZ distance, right? So this is the actual distance, 0.0050026. So I think 0.005 is the correct size. So let's extrude this plane. Extrusion along Z, 0.005. Okay. Now if I look at in this direction, you see that it's perfectly touching. And that's now pretty good. You see that if I didn't add this section here, the contact between this plane here and this face is very just one line. It's a linear contact here, so that will cause a lot of problems during the first stage of the simulation. And now my model is looking very good. Now there's still one phase to do, which is a bit boring, is to create the groups, so the mesh groups. And the problem with this model is that I didn't do it 100% from the geometry. So I cannot do like I'm doing usually, you know, create group from geometry. So I'll have to create some of the group manually using a filter. So let's do this right now. So let's go to this, what is it? Mesh, create group. Okay. Now let's select this mesh set here. I don't know why it's not selecting. Okay, mesh 2, that's it. And let's create some surface first. So face, the name will be load face, and enable manual edition, set a filter, and now you have to find a way to select those elements. So what I'm usually doing is that I'm using this coplanar faces. Then I can select one element of this and applying not an idea mesh face. Okay, so there's a, okay, that's, you have to click in threshold value first and then you click on the element. Yeah, and now it selects the whole face. So when this face is selected, click on add to add the element IDs of all the faces. Click on apply and you created one mesh group for this. Now let's repeat for the group of the contact surfaces. So let's, how do I do that? Let's hide my mesh 3 here. Let's hide all of this. Let's hide the plate. Rotate. Let's rotate a bit this. If it allows me to rotate. The comments are a bit erratic. So now I need to select all those faces here. So setting, I know if I will be able to use the same technique on art. So I created the mesh 2. Mesh 2 face, set filter. Okay, I don't know why it's not selecting anymore. Okay, let's close this window. Let's open it again. Group on filter, maybe that's the thing. So I have selected this. So I don't think it works if I select two. If I select only one, it should be working. So now it's selected all of this, and so I want also those here. So how can I do that? Well, the way, so let's call that contact 1. Apply and close. You see that it appears here, and what I can do is I can edit this group as a standalone, and now I can add some elements to this. So I'm basically going to select all those elements one by one. So that's what I told you, this is a bit tedious. It's much better when you have some kind of geometry. The selection of the mesh groups is very tedious. So now I added that. So apply and close. So if I activate this, yeah, so this should mean this is the first contact face. Now let's do the same for the other side. This will be contact 2. There's probably a way to to combine the filters so that it selects a bit more, but I've never found how to do this. So if you have some clue on that, please let me know. Apply and close. Okay, apply and close. Edit as standalone, and now I'm gonna just add those contacts here. Apply and close. Okay. Now you have to ask yourself the question too, is that if this enters in contact with the plate, will the contact here be sufficient, or will I need to increase a bit this contact of surface? I think should be sufficient, but we'll see. In case it is not, I can still modify that later. Okay, so I have the load group, I have the 2 contact group. Now I need another group for the volume of this. I think I not remember exactly why I need that, but I remember I need it. So let's create a group. So this one is easy to create. A volume mesh 2, and I just have to select all. This will be spring vol. Okay. Now let's create the groups for the plate. So let's reactivate the plate here. So I need also some contacts on this plate, and I need so I need the top face as a contact surface, and I need also, I will fix those 2 edges here and here. So I need also 1, 2, 3 groups. So let's do that. Create group. So the first group will be face, group on filter, add coplanar face to this element, apply, this will be plane contact. Now let's add another one. Face. Now I need to select those, so group unfiltered. Does it work if I select like with let me try that. Didn't really select everything, and it selected some of the top elements. Yeah, it didn't work. So it's a bit, that's why it's a bit tricky. You need to. Okay, so now I selected that, but I selected also those. So that's why finally I always get in with manually selecting everything, because it's just easier. Okay, let's add that. Let's do the same on the other side. Okay, good. So that will be let's call that fixed plate. Apply and close. And now I want also the volume of the plate. So let's create volume, select all. Now let's check that my groups are okay, and if this is, I should be good to go. So let's hide my mesh. So let's check load face. Yeah, good. Contact 1, yes. Contact 2, yes. It might be easier if I merge those two groups actually. So I don't know if I can merge groups. Can I do that? Construct group, edit, union groups. Union groups, looks like that's what I want to do. Contact 1, like, let's call that spring contact. Okay, cool. So now I have one group with the two. That's even better. Okay, let's have a look at the volume. Yep. Let's have a look at the plate. So this is the top. Fixed plate. Yep. And plate volume. Okay. So now I have everything I need. So now I have two mesh groups. The mesh 3, which is my plate, and the mesh 2, which is my spring. What I'm going to do is that I will merge those two. So to merge those, you have to use the build compound mesh function. So select the two mesh. So we'll call that spring plate. And don't forget to, so uncheck this. I don't want to merge the nodes, otherwise I'll have a problem with the contacts. But I want to check this function, create groups from input objects. So I'm getting all the groups I defined for each in one mesh set. And this is the final mesh for the simulation. So as you saw, there is a bit of work on the meshing on this example, much more than for the previous spring, because here I really need to have a very, very good mesh for the contacts. Let's save that. And just in case, you know, I get an error or something, let's export that into, so first time I call that this, let's call that 2. Okay. And now we are ready for the second phase, which is going into Codaster, setting up the contact, and just looking. So before we go into Codaster and set up the model, it's good to have a look a bit at the documentation which is available on the website about contact and friction, because contact is really something tricky to set up in Codaster in general. So you really need to give it some thoughts. So this is the PowerPoint which is available. As usual, it's not very easy to read, so you really have to take the time to understand what is written. I'm not gonna go in the theoretical aspect. I'm just gonna show you what is important in this. And basically, what I'm gonna talk about is the general recommendation about master-slave, the choice of the algorithm and formulation. You have to take maybe the most important page in this presentation is this page here. It's basically what is telling you what you should be using. So you can see that those are the main types of contact you can define. You have 3 types of discrete contacts and 2 types of continued contact. And the main difference between discrete and continue is that discrete continue have better performance. So which means that they will, when you use a discrete contact, it will be easier to converge and you will get faster solution. But they are less reliable, which means that probably the result that you will get out of those will be less, less accurate, because I don't know, the stress at the contact interface is not that well represented, or I don't know. It's basically like that. And if you use continue type, the performance decrease, so which means that it will take longer to converge, but the reliability is better, so you'll get better results. Now there's also difference in the degree of freedoms that it allows. So discrete types basically are more limited. So if you use discrete penalization, for example, or discrete contrainte, so stress, you'll need either from hundreds of degrees of freedom or thousands of degrees of freedom. This one, discrete GCP, is limitless, so it's a bit better. So if you want to use discrete and you have a lot of degree of freedom, then you use this. If your degree of freedom are around hundreds or around thousands, then you can use those 2. Now, if you have friction, you have no choice. There's only one type of contact that supports friction. It's the discrete penalization method. And by the way, this is the method I am going to use here in this example, discrete penalization, because this one is very powerful. And if you do not have friction, that's when you can use the other types. Now, there's also one thing, if you have incompatible mesh, so you have, for example, you use tetra elements on the top in the spring, and you use hexa element on the plate like I did on my first model. In this case, you have no choice, you have to use the LAC method. The LAC method is, it's much more reliable, but it's very slow, and it requires you to use special method to divide the mesh. So it's explained, I think, at the end of this PowerPoint. There is a method called, I don't remember what it's called. I think it's at the end. Yeah, this method, découplac. So you will need to use this découplac to automatically splits the surface of the cube which is in contact and create something like this that will be used to calculate this method. So that's a bit more annoying. Okay, we have talked enough about all of this. Let's go back to practical stuff and let's actually calculate our model. So let's go into Aster study. And I'll have to do a bit of modification to my mesh. So if you remember, I had only one material for the spring defined before. So what I'm going to do is create a second material. And also I have to do a bit of change on this steel material as well. I actually, if you remember, I input the hardening curve, and the thing is, so this was my data for my hardening curve, and I need to be I need to have the same elastic modulus, you know, to connect the 0 to my hardening curve. So now I should have I have the right elastic modulus. It should match the initial value of the hardening curve. Now let's create another material for the plate. So Debugging Material. This will be elastic. And this time I want 2.6, and I want it to be a lot more rigid. So instead of power 11, I'll put power 13. That way I'm sure that it will be much more rigid than the spring. So the plate will almost not deform. That's what I want. 0.3. Let's call that rigid. So here I have to change this as well, because in this function here I'm telling that I'm associating this material to everything, which is not true. I'm only associating to the spring volume. And I'm associating the rigid material to my plate. Okay. So now those material are defined. So now we need to define the contacts. So let's go into Defi contact. It's here, and that's where the most difficult part is. So we need to give it a formulation. So I'm going to use discrete. We need to give it so frottement is the friction basically. So I don't have friction, so I have to select sans. Sans means without friction. And let's choose the algorithm. Let's select the zone first. The zone is where I define the slave and the master contact. So this is the master. The master will be the plate, so this will be the plane contact. Yeah. Okay. And the slave faces will be spring contact. Okay. Oh yeah, so that's the most important option. Penalization, that's where you select penalization, and there you see here you have this coefficient. So the setting of this coefficient is actually pretty important. So let's click on the documentation. So if you look for the method of penalization and this EN coefficient, it tells me that this is the coefficient of penalization on the interpenetration for the penalized method. It is homogeneous with the stiffness of springs placed between surface of contact to prevent the interpenetration. A value about the largest Young modulus of the solids in contact multiplied by a characteristic length is initially recommended. One will increase the value of the coefficients until obtaining stable results. Okay, that's what it tells me. So if I think about the largest modulus, so if you remember, I took 213, and the characteristic length of the model is 0.001 or something. So if I multiply that by should get around this value. So 3, 3, 3, 2. So I'm missing 3, 0 here. Maybe I can enter it like this. Okay, so let's see if there's other things I need. So I think all the other things are advanced options. So maybe I will activate the lissage. Other options, React, geom automatic control without. I think this is to control the orientation of the normal between the contact face. So we don't need that because the normals are very aligned. Okay, let's try with this contact and let's see if that works. So I got my contact, let's save. And basically I got in, let's go into stat nonlinear. Let's activate the contact and select my Defi contact I just created. And now one thing that I want to do is that if I start with the current times that I have defined before, so 100 increments, and the interval is very large going until 1, so this will, there's a big chance that this will not converge. So let's try first to go up to 0.1. That way it will I have much better idea of the convergence. Yeah, and I need also to change the storing function, which will go up to 0.1 and store only 20 value. Okay, now it's show time. It's time to calculate and see if I will get something out of it. Okay, so it's red, and I think I remember I understood right away what problem I did. The group back contact spring ne fait pas partie du maillage mesh. Okay, yeah, I completely forgot about that. So this is a big mistake, but you see it's easy to correct. The thing is that I changed the mesh just like this. So I switched to this spring plate, but I forgot that in the process of changing the mesh, I have changed the name of some of the contact groups that I have defined before. So I have basically to go back on those mesh sets where I have used the contact groups. And so those are the boundary conditions. So spring vol, I think I called it the same. So let's go on to this one, for example. So I have no more contact spring. Instead, I called it spring contact. Okay. And this one, load face, I think the name is the same. This one, yeah, it should be okay because I just defined that. And yeah, here there's no groups. So everything else should be okay actually. Let's try again. Let's look again at the error message just to be sure. So contact spring, yeah, the error was here. So let's try again. Let's calculate again. So it looks like it's launching the calculation, which is a very good sign. Oh, I've talked too early. So what is the problem this time? Normal non sortante. Let's have a look. What is the problem? In the group spring contact, there are two. Okay, so the elements in the spring contact group are not oriented correctly. Okay, so I have to use modimaillage to orient them in the right direction. Let's try that. Let's go back here. Modimaillage. Let's select my mesh. Let's orient 3D. And let's use spring contact. I think that's the one. So I guess that should do the trick, I hope. Let's try again. So as you see, it's a very much a trial error process where you see which kind of error you get and you correct the error. So of course it helps to understand French because many of those error messages are in French. But you know, in the forum you have also a lot of people that can, you know, tell you which error is what. Okay, so now I'm getting another error. Okay, the traction curve. Oh yeah, okay, I know what this is. I created a second material rigid, but I forgot to give it the traction curve. So even if that material will never go in elastoplastic, this material will also need to have a traction curve. So I need to define to modify this rigid material and add traction. Hardening curve, do it. Okay, let's go back, let's try again. So, will it finally start to solve? My computer is starting to run. I can hear the fan, and I am starting to see some Newton iterations here, so it's a good sign. So now the main problem is that will it converge or not, and this, you know, is pretty much depending on the definition of the contact that I have defined. I know the other parts, like the elastoplastic material, works because I've done those previous simulations before, so I'm sure the error will not come from here. Okay, now I know it's red, so let's see what is going on here. So if I look at the error message, it tells me that my matrix is singular, and you know, when this kind of thing happens, basically you have a problem on your boundary condition somewhere. And I just remember another mistake I've done is that, okay, I've changed the name of the groups I used, but I didn't have the plate right in the first simulation. So I have not actually fixed this plate. So the spring is going on, but the plate here is not constrained. So that's why I'm getting some problems, I guess. So yeah, so that's annoying. So I have to go to my boundary condition where the spring is actually fixed. And actually I don't want to fix the spring, right? I don't need to fix those faces anymore. So that was my mistake. The spring should not be fixed. Instead, what should be fixed? It's the plate contacts. No, sorry, not that. The fixed plate. Yeah, that's where this boundary condition should be. Yep, so now that I have correct boundary condition, I hope that I'm going to start to see something. Aha. Okay, so this time I'm starting to see iterations, so that's a good sign, and it's even a better sign if those iterations start to converge, and they do, because it's written here, critère de convergence atteint, which means that the criteria of convergence is reached. So now I basically just have to wait, and so I don't know how long this will take, so I'll just wait a bit. So we have 2%. Maybe I used a bit too much iterations because I'm just calculating 10% of the whole time. But we'll see. So let's wait a bit and come back when it's finished. Okay, so very good news. My simulation finished at 100% and converged totally. So let's have a look at the results, and let's see if this is what I expect, because I might have some surprises. Let's open Parvis. Let's load my results. Let's add filter, warp by vector. Let's look at the displacement. Okay, so let's rescale according to last time step. So you see almost no deformation, and I think that's because I calculated only very small deformation. So if I increase a bit the scale factor, yeah, so that's the, you know, the very deformed shape. But here, so it worked. You see, it went down and it slided, but it's just that the deformation now it's so small that you can't really see it yet. So if it goes down a bit, and that's all. So not very impressive for this first run, but this is only a test run and it converged. So now let's try with the actual loading that I wanted to put on it. I think I wanted to put a displacement of 7 millimeter. Let's go with I don't know, with 4 millimeter down first to start. I'm not so optimistic if 7 millimeter is a bit too much. So let's have a look. Yeah, so I was really calculating a displacement which is very small, so that's why. And I only calculated 10%. So let's go with 4 millimeter down. And let's change, not this, the number of increments, so until 1. And I have 100 increments on the whole time. I'm wondering if it will not be enough, but anyway, if it doesn't converge, it will automatically divide the increment by 2. So I think I'm just gonna try that. And let's change also the storing function. Okay, and let's launch again the calculation. And now we'll see if we have some problems with convergence. So in this case, it didn't converge, and I got an error message that I need to increase the number of increments or the number of iterations. So this is fine because 100 increments for such a large number of time steps, it's actually quite a gamble for this kind of simulation. So I'm gonna do two things. One, go into stat nonlinear and increase the number of iterations. So I think it's here in Convergence. I'm gonna increase that to 40. And I'm gonna go into my increments and I'm gonna increase the number to 120. So I will do like that until I reach the convergence. So that's again some kind of trial error process, and it's very much depends on a lot of things like the contacts, types, all those parameters I inputted on Defi contact, the quality of the mesh, etc. So there's a lot of things that will influence the convergence. Let's try again the mesh and let's see if I can get it to converge this time, or if it still doesn't converge, I'll have to change again some of those parameters. So that's the difficulty about nonlinear simulation in general, and a simulation like that which integrates several types of nonlinearity together is very, very complicated. So you really have to understand each of those parameters and to play with the convergence and the number of increments and all of that to make sure that you reach the convergence. Let's wait again and let's see. Okay, so after a lot of different tries, it still didn't want to converge. So I was getting this kind of message, so which means basically, because it's in French, the behavior law is failing. So you have to find a way to verify your parameters, the coherence of the units, maybe increase the number of iteration, or so this is basically what it's telling. And if you look at the code here, you see that the Newton's iteration are basically failing after a certain number of time steps. So it was failing at 30% of my simulation. It was going up to 30% of the time and then just failing. So I finally understood where this problem came from. So I was thinking, instead of doing all over this video tutorial with the right answer, it would be much more useful for you. So I just continue on what I did and show you the solution, because you will very surely find the exact same problem on your simulation if you use Contact and Codaster. And so let's go back, and the main problem is so there are two problems. One is the number of iterations, which is always important in nonlinear static. The second problem is the contact definition. And I'm using the penalization method with discrete contact, like I described before. And basically, all the parameters you can define here are not that important. Those are just advanced settings that do not really make any change. So I tried a lot of those, and it didn't really change anything. The biggest problem here is the value I have taken for the penalization coefficient. So it's just too high. And the problem here is that in this, so I used the recommended value, right? I took the higher Young modulus value multiplied by characters length of the model. But the problem is that one of my object is really more rigid than the others. So I increase the stiffness a lot, which means that this value here for this coefficient is much too high if I use the recommended value. So I did some tries, and if I decrease this to, let me see, 2 power 6, yeah, so it's still 1, 2, 3, yeah, so 2 million. If I decrease this value to 2 million, it converges, so with the correct number of increments again. So I'll change that right after. So a quick explanation is that the penalization method is a method in which the nodes of one part are linked to the node of the other part using some invisible springs. And this value here is similar to the spring, tension coefficient, the spring coefficient. So if this value is high, the result you're getting is more accurate because you will get less penetration of one part into the other, but it will be much harder to converge. So generally when you do this kind of penalization method contact simulation, you have to do a few tries to understand what is the right coefficient for your simulation. And there is a methodology to do this kind of tries in Codaster, but it's a bit too much for this video, so I'll make another video about it, just about this, after that. So just watch my YouTube channel for this video if you're interested to know how to optimize this coefficient. Now let me take this value for this simulation. So okay, and let me change the steps. So I have done, so here, where is it? Diffie list, not this one, sorry. Yeah, this is my time step, and basically I have divided the time from 0 to 1 into a certain number of time steps. So if I go from 0 to 0.25 with 30 time steps, it works. If I go from 0.25 to 0 with 60, it works. And here I have to increase a bit the number of time steps to 100, I think 100 was the right number. Okay. And now there is another important thing that I discovered, is that there is a very useful PDF, which is even better than the training material that I talked about in this video, and it's this document here. So it's this one is the French version, so I'll show you the English one. Note of use of the contact in Codaster, and it's the document U20404. So search for that and make sure you find the right version. So here, for example, it's not the last version. The last version is the one from 2018. And this document is really detailed, so it's really great document. It gives you some useful advice about how to make your simulation converge, and it is written with phrases, so not like the training where you have to guess what it means. Here you really have some explanation. Now, of course, the English version is not that good, so if you speak French, read the French version, which is really much better. But that's the problem with Codaster. You have to, if you know French, that will be much better for you. So for example, if you go down to the very end of this document, there is a whole section telling you how to optimize your discrete contact formulation. And here, for example, it tells you if you have great deformation, great displacement and contact, there are some things that you need to change into your Newton method. So let's do that in this model, just to be sure the convergence will be better. So the first things to do is to go into my nonlinear, then open my Newton method, and the recommended predicament is I have to set a Bragg iter to 1. So this basically means that the matrix the stiffness matrix will be actualized at every Newton step. So that's why it's 1. If I put 2, it will be reactualized at every 2 steps. So more here is not better. It's 1 is the best value here. Now, if you use prediction elastic, it's also better when you use this. So I remind you, this is when you have a simulation when you have contact plus elastoplastic material, like in this case. Then you can use gradient deformation. So this is set up, and what it's telling you also, if you use gradient deformation and this low here, the tangent matrix is non-symmetrical, so you have to set up symmet equal no. So just activate this option here without checking that. Yeah, and I think, well, there's much more in this document, and really you should have a look, read it. It's really detailed. And read the last version, the one from 2018, which has been corrected by Zifa Kudao. So this is the last one I could find. So, and this document is really, really good. Okay, and so let's activate that, and let's save this. And I still had one thing I really wanted to show you. Let me think quickly. Yes. In here, when you do nonlinear analysis like that, one thing which is very difficult is you don't know what is the value of displacement in the contact area when you solve. Well, there is a good news about it. There is an easy way to get the value of contact at a specific node, for example, during simulation, so without having through Paravis or anything like that. So it's really useful. So let me show you how to do this. So you have to go into the mesh, and what I'll do is that I will add a group node, let's say at this location. So let me add create group. Let me add a node here. This will be manual selection. Let's select this node here, and let's call that A1. So I add it. Okay, so I added a node here. This node, I will use it in the Aster definition in the stat nonlinear. You have something called suivi DDL. So this will allow you to follow up the results from one node during the simulation. You'll see where it appears when I start to solve. So the feed I want to follow is a displacement. I want to follow it from this node that I just checked. I want to get the displacements dy in the y direction, and what I want to have is the value of this displacement. So you can even get the maximum or the minimum or stuff like that. So pretty useful stuff. Okay, and now I'm ready to solve, and you'll see that I will get now convergence of the solution and a way to follow up what is happening. So let's wait a bit that it starts the Newton iteration. And it becomes a bit larger, so you have to expand a bit. And this column here has been added. So this is what I just created, the suivi DDL. So suivi means in French follow. So you follow the degree of freedom of the node that you checked out, and you have the value of the displacement dy directly written in this table here. So this is pretty cool. So if you want to be sure there is no penetration, for example, at this node, or anything like that, you want to be sure of the accuracy of your results, this is pretty good. So now this simulation will take quite some time because it's a nonlinear one, and the convergence will take at least, I think, 15 or 20 minutes. Yeah, don't forget to change the time you put here. The default time is 15 minutes, so you know, it happens that you check, you launch a simulation, you come back 15 minutes later, and you know, the solution just stopped because the time was not sufficient. So make sure that this is set up correctly. Okay, and now let's wait for the final solution, and then we'll have a look at the results. Okay, so my simulation is finally finished, and as you can see, it converged 100%. So I will now be able to show you the results. So let's go into the case view, let's go into Parvis. And let's load my results. Apply, and let's apply the filter to see the deformation. Warp by vector. Let's have a look at displacement. Let's go from the start, and we now see that, okay, spring is deforming until time 1, so everything is fine. Let's rescale the data so that it doesn't appear full red, and you see the final deformation is 4 millimeters, so that's what I wanted for this simulation. Let's have a look at the von Mises stress. Yeah, looks great. Now let's quickly have a look at the value of the stress, just to make sure that this makes sense. So let's select one node in this region here where the stress is maximum. Here activate the signal in the selection display inspector, and the first value you see here is the von Mises stress. So it's around 336 MPa, which is reasonable. Now let's activate the animation view. So I'm at the last time step. So if I look at the value over the time step, so it seems to stay reasonable. It's not going to be extremely huge. So the value, the maximum value of the stress go over 490 MPa, and you know, this is a nonlinear material simulation, so this is perfectly fine. So result seems to make sense, and that means that this video and tutorial is finished. So I hope you learned a lot from it. I'll try to do a bit more videos that will relate to this one, because there are still a few tricks that I would like to show you, like how to monitor the results more efficiently, how to do analysis of the penetration coefficient. That this is very important. Maybe talk a bit more about different types of contacts. So those are, you know, additional videos that I'm thinking about to make. So if you like all of this, you think it was useful, please leave a comment, let me know, give it a like. This is always appreciated, and thank you so much for watching this video.